work that we do in our group is broadly characterized as crystal engineering. In particular, we work with a group of materials called zeolites. Zeolites are aluminosilicates. They form in nature, but they're also used in a wide range of applications, such as catalysis and separations and things like ion exchange and detergents. And they're even being explored for aspects of drug design and diagnostics. This is an example of a zeolite. Zeolites, one of their unique features is that they contain very, very small pores. As you can see here, these channels. So molecules can essentially enter these channels, and inside the channels are sites where they can react and basically convert into other materials. So where our group comes into this is we look for ways that we can rationally design these materials. Usually when zeolites form, we would typically characterize them as poorly engineered, in the sense that these channels that form tend to be oriented along the longest dimension of the crystal. So when molecules come, they have to travel a very large distance through these materials, and that can lead to problems in terms of their efficiency, and can also lead to problems in terms of deactivation, so molecules become trapped in here and block the pores. So what we try to do is we try to engineer these materials so that they have very small diffusion path lengths. Okay, so the dimensions of these crystals are less than 100 nanometers in thickness. And to do that, we use a technique that's very common in crystallization. We use what are called zeolite growth modifiers. Now, these modifiers are molecules that basically target specific surfaces of the zeolite. So each zeolite, or each crystal, more broadly speaking, has different crystallographic planes. And so we try to find molecules that have a recognition for binding to a specific surface. When the molecules bind to the surface, they block other growth units from coming down. Okay, so crystals growing in that direction are essentially impeded, and as a result we can selectively tailor how these crystals grow in different directions.